In 2018, a spacecraft launched in 1977, running on computer power weaker than a modern calculator, crossed into interstellar space and saw something its twin, launched 16 days later, was completely blind to. Not because the twin wasn't there first. It was. It crossed that same boundary 6 years earlier. But by the time it did, one of its most important instruments had been dead for over 30 years. So when Voyager 1 slipped past the edge of our solar system in 2012, it had no working plasma sensor. It felt the boundary. It did not see it. Voyager 2 did. And what it saw rewrote what scientists thought they understood about the edge of our solar system. This is the story of what Voyager 2 found that Voyager 1 completely missed, and it's a story that, decades later, is still being written, one faint signal at a time. Think about that for a second. 2 spacecraft, built in the same facility, launched from the same coastline, carrying nearly identical instruments powered by nearly identical nuclear batteries, aimed at nearly the same destination beyond the edge of everything we call home. And yet, because of one component failure decades apart from the moment it actually mattered, these 2 machines ended up telling humanity 2 completely different stories about the same boundary. That's not a footnote in space history. That's one of the most important accidents of timing in the entire history of planetary science. To understand why this matters, you have to understand what these 2 spacecraft actually are. Voyager 1 and Voyager 2 are twins, built side by side, launched from the same site months apart in the summer of 1977. Voyager 2 actually left Earth first, on August 20th. Voyager 1 followed on September 5th, but it took a faster, more direct route through the solar system, and it overtook its twin in December of that same year. From that point on, Voyager 1 became the record holder, fastest, farthest. First to reach interstellar space, Voyager 2 took the long way. It flew past Jupiter, then Saturn, then kept going, becoming the only spacecraft in human history to fly past Uranus and Neptune. Nobody else has ever done that. Nobody else is scheduled to. Before either spacecraft ever reached that far edge of the solar system, they had already rewritten the textbook several times over. Voyager 1 flew past Jupiter and discovered a thin ring circling the planet that nobody had confirmed before, along with 2 brand new Jovian moons. At Saturn, it found 5 previously unknown moons, and an entirely new ring, one that scientists came to call the G-ring. It was the mission that first showed us Jupiter's moon Io as a living volcanic world, spewing sulfur into space, nothing like the dead gray moon orbiting our own planet. It was the mission that gave us our first real look at Saturn's moon Titan, a moon wrapped in a thick, hazy, nitrogen-rich atmosphere that reminded scientists eerily of early Earth. Voyager 2, meanwhile, was doing something no spacecraft before or since has ever managed. It used the rare alignment of the outer planets, alignment that happens only once every 175 years, to slingshot itself from Jupiter to Saturn to Uranus and finally to Neptune, using each planet's gravity to fling itself toward the next. In doing so, it became the only spacecraft in human history to fly past Uranus and Neptune. At Uranus, it discovered new moons and rings and measured winds, and a magnetic field so oddly tilted that scientists are still trying to fully explain it. At Neptune, it revealed the Great Dark Spot, a storm system larger than Earth itself, along with more of the planet's moons and rings. Nothing else we have ever built has been close enough to either of those ice giants to see them like that. Nothing is scheduled to get that close again for decades. By the time both spacecraft finished their planetary tours, in the late 1980s, NASA gave the mission a new purpose. It became the Voyager Interstellar mission, a fresh chapter with one central goal: to keep pushing outward past the last planet, past the reach of the sun's light, and to measure, for the first time in history, what the true boundary of our solar system actually looks like from the inside out. Both spacecraft carried a suite of scientific instruments designed to measure the environment around them: magnetic fields, cosmic rays, charged particles, and critically, plasma. Plasma is the 4th state of matter, a hot soup of charged particles that makes up almost everything between the stars and everything blown outward by our sun. If you want to know whether you've truly left the bubble of our solar system, plasma is one of the most direct ways to check. The instrument that measures it tells you the temperature, the density, the speed of that material around you. It is, in a very real sense, the sense of touch for a spacecraft floating through the vacuum of space. To picture the heliosphere itself, imagine our sun as a ship sailing through the galaxy. As it moves, it constantly blows out a stream of charged particles called the solar wind, and that wind inflates a massive bubble around the entire solar system. A bubble that stretches out past every planet, past every dwarf planet, past regions of space most of us never think about. Inside that bubble, the plasma is hot, but thin and sparse, shaped entirely by the sun's own activity. Outside that bubble, in true interstellar space, the plasma is different, colder in temperature, but far denser, shaped instead by the leftover material from stars that exploded millions of years before our sun ever formed. The heliopause is the seam between those two environments, the place where the pressure of the solar wind finally gives way to the pressure of everything beyond it. Scientists had drawn this boundary on diagrams for decades before either Voyager ever got close enough to actually test whether the diagram was right. And here's the twist that most people don't know. Back in 1980, right after Voyager 1 flew past Saturn, its plasma instrument stopped working. It simply died. Voyager 1 kept going. It kept transmitting data on magnetic fields and cosmic rays, but its ability to directly sense the plasma around it was gone, over 3 decades before it would need that instrument the most. Fast forward to August 25th, 2012. Voyager 1 crosses the heliopause, the boundary that separates the bubble of particles blown out by our sun from the vast ocean of interstellar space beyond it. This is one of the most significant moments in the history of space exploration. A human-made object leaves the solar system for the first time. It's a headline that ran everywhere, but because its plasma instrument had been dead for 32 years, Voyager 1 crossed that boundary essentially numb. Scientists had to infer what was happening around it, using indirect methods, using other instruments that could only estimate plasma behavior rather than measure it directly. It was like watching someone walk through a doorway blindfolded. You know they went through. You don't fully know what the room on the other side actually feels like. Researchers didn't give up trying to understand what Voyager 1 experienced, though. Instead, they got creative. One team relied on a completely unrelated instrument, the plasma wave subsystem, which listens for radio emissions rather than directly sensing plasma the way the dead instrument once did. When the sun sends out a burst of material toward the outer solar system, that material can trigger oscillations in the surrounding plasma, and those oscillations produce a faint radio signal that a working instrument can pick up from millions of miles away. By timing when those oscillations happened and comparing them to when solar outbursts left the sun, scientists could indirectly calculate the density of the plasma around Voyager 1, almost like guessing the depth of a well by timing how long it takes an echo to come back. It worked. To a degree, it gave researchers a rough picture, but a rough picture built from an indirect method is never the same as a direct, continuous measurement from an instrument built specifically for the job. That's the gap Voyager 2 was about to close. Voyager 2 did not have that problem. On November 5th, 2018, 6 years after its twin, Voyager 2 reached that same kind of boundary at a different location, at a different point in the sun's activity cycle, and its plasma instrument was still alive, still working, still sending back real numbers. For the first time in human history, scientists had a direct working plasma sensor riding along as a spacecraft crossed out of our solar system and into the space between stars, and what it showed them was not what they expected. The first thing Voyager 2 revealed was something Voyager 1 physically could not have shown scientists, because Voyager 1's dead instrument gave them no choice but to guess. As Voyager 2 approached the heliopause across a stretch of roughly 140 million miles, its plasma sensors picked up something scientists could finally watch happen in real time. The plasma around the spacecraft began to slow down. It began to heat up. It began to grow denser, not as a sudden wall, not as a sharp line in space, but as a gradual, measurable transition, a kind of pressure building the closer the spacecraft got to the true edge. This is something researchers had theorized about for years, but Voyager 1 never had the instrument working to confirm it directly. Voyager 2 did. It watched the border approach, like watching weather change before a storm arrives, and for the first time, that process was captured in real plasma data instead of inferred from second-hand readings. Then came the second discovery, and this one surprised almost everyone involved. When Voyager 2 finally crossed fully into interstellar space, its instruments measured the temperature of the plasma on the other side of the boundary. And it was hot. Not hot in the way we experience heat here on Earth, because this plasma is so thin, so diffuse, that a spacecraft sitting inside it wouldn't feel warm at all. But by the physics of particle energy, the interstellar medium on the other side of the heliopause measured out at over 54,000 degrees Fahrenheit. That is dramatically hotter than models had predicted. Scientists had pictured interstellar space as cold, quiet, and largely undisturbed by anything happening near our sun. Voyager 2's real, working plasma instrument proved that picture wrong. The material out there is hotter, more energetic, and more complicated than anyone modeled it to be. And again, this is a number Voyager 1 could never have handed back to Earth, because it had no way to directly measure it. The third finding is maybe the most visually strange one, and it's about the shape of the boundary itself. Scientists had assumed going in that the heliopause would look roughly the same no matter where a spacecraft crossed it, like the surface of a bubble that's basically uniform in thickness all the way around. Voyager 1's crossing, back in 2012, showed something researchers labeled a thick boundary layer, a wide, gradual zone in the inner heliosheath before the true edge. When Voyager 2 crossed 6 years later at a different location, further around what scientists picture as the flank of that bubble, its data told a completely different story. E. Voyager 2 observed a very thin boundary layer, a much narrower, more compressed transition zone compared to what Voyager 1 experienced. Same star, same solar wind, same general structure of the heliosphere, but two very different textures depending on exactly where you cross it. Voyager 1, sitting alone with its single data point, could never have revealed that this asymmetry even existed. It took a second spacecraft with a second working instrument, crossing at a second location, to prove that the edge of our solar system is not a clean, uniform sphere. It's lumpy. It's uneven. It behaves differently depending on where you poke it. And then there's the finding that scientists have nicknamed the leaky heliosphere. One of Voyager's other instruments picked up something remarkable as Voyager 2 approached and crossed the boundary. Particles from inside our solar system, material blown outward by the sun, were found slipping out through the heliopause into interstellar space. And going the other way, particles from interstellar space were found trickling inward, seeping into the heliosphere itself. The boundary that separates our solar system from everything beyond it is not a sealed wall. It's porous. It leaks in both directions. Voyager 1 had actually hinted at something like this on its own crossing, detecting tendrils of interstellar particles that had pushed their way in before it even reached the official boundary, almost like roots pushing through cracks in rock. But it was Voyager 2, with its working plasma instrument backing up the picture, that gave scientists confirmation this leaking wasn't a one-time fluke. It was a real, ongoing exchange happening at the edge of our solar system, material constantly crossing in both directions, all the time, right now, as you're hearing this. There's one more piece to this story, and it might be the most important one scientifically, because it's the one place where Voyager 2 didn't contradict its twin. It confirmed it. When Voyager 1 crossed the heliopause back in 2012, its magnetic field instrument picked up something nobody expected. Scientists assumed the magnetic field just outside the heliosphere, out in true interstellar space, would look dramatically different from the magnetic field inside it. Instead, Voyager 1 found that the magnetic field just beyond the boundary was lined up, running roughly parallel to the magnetic field inside the heliosphere. At the time, scientists had no way to know if that was a real pattern or just a coincidence tied to exactly where and when Voyager 1 happened to cross. One data point isn't a pattern, it's an anecdote. When Voyager 2 crossed 6 years later at a completely different location, its own magnetic field instrument measured the exact same thing. The fields lined up again. That single piece of confirmation turned a strange coincidence into a real scientific result. It told researchers that this magnetic alignment isn't a local quirk. It's likely a genuine, large-scale feature of how our sun's magnetic environment interacts with the magnetic field of the galaxy around it. Without Voyager 2 arriving with working instruments, scientists would still be unsure if Voyager 1's strange reading meant anything at all. Step back for a second and look at the full picture here. Voyager 1 gets all the fame. First human object in interstellar space, farthest spacecraft from Earth, the record holder, and it deserves that recognition. But because of a single dead instrument 3 decades before its most important crossing, Voyager 1 went through the most significant boundary of its entire mission, almost completely blind to the one thing scientists most wanted to measure there. Voyager 2, quietly, without the same headlines, without being first, carried a working plasma instrument through that same kind of crossing, and handed scientists the first real, direct look at what that boundary actually is. It measured the gradual buildup of pressure approaching the edge. It measured a temperature outside the solar system far hotter than anyone predicted. It revealed that the boundary isn't a uniform shell, but a lumpy, uneven surface that looks completely different depending on where you cross it. It confirmed that material leaks through that boundary in both directions, all the time. And it confirmed that the strange magnetic alignment Voyager 1 detected wasn't a fluke, it was real. None of that would exist if Voyager 1 had been the only spacecraft to make that journey. Every single one of those discoveries depended entirely on Voyager 2 surviving long enough, staying functional enough, and having a plasma instrument that never failed. That's not a small thing. These spacecraft launched in 1977. They are running on radioisotope power sources that decay and weaken every single year. They are managed by teams at NASA's Jet Propulsion Laboratory, who have spent decades slowly shutting off instrument after instrument one by one, just to conserve enough power to keep anything, transmitting back to Earth. Voyager 1 has already lost multiple instruments to age and power limits. Voyager 2 has had its own scares, including a moment where it briefly lost contact with mission control entirely. Both spacecraft are now traveling on borrowed time, and yet both are still, right now, sending back real data from a region of space no other human-made object has ever reached. There's also a subtler point buried in all of this, one that rarely makes it into the headlines. Voyager 1 crossed the heliopause during a period of relatively low solar activity. Voyager 2 crossed 6 years later, during a completely different phase of the Sun's roughly 11-year activity cycle. Researchers going in genuinely expected that difference to matter, that the boundary itself might sit at a noticeably different distance from the Sun, depending on how active our star happened to be at the time. Instead, both spacecraft ended up crossing the heliopause at strikingly similar distances from the Sun, even though the solar conditions around each crossing were so different. Scientists studying the data openly admitted they don't fully understand why that is. It's one of those findings that doesn't resolve into a tidy answer. It just adds another layer of complexity to a boundary that keeps behaving less predictably the more closely it gets studied. It's worth pausing on how differently these two crossings actually looked. Voyager 1 sailed roughly 10 additional astronomical units farther than Voyager 2 needed to travel before it reached its own heliopause crossing. An astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles, so that difference alone represents hundreds of millions of extra miles that Voyager 1 had to cross before finally breaking through. Researchers at the University of Iowa, who have spent years studying the plasma wave instruments on both spacecraft, compared the experience to two people walking up to an elephant with nothing but a microscope. Each person examines a tiny patch of skin, and each person walks away with a completely different impression of what an elephant actually is, because neither of them can see the whole animal at once. That's essentially the situation scientists are in with the heliosphere. Two data points, gathered years apart, at different locations, are the entire foundation of what we know about the shape of the bubble surrounding our solar system. Every new comparison between Voyager 1's readings and Voyager 2's readings adds a slightly larger patch to that picture, but the whole animal is still, in a very real sense, invisible to us. And this is where the story becomes bigger than just one crossing in 2018, because both Voyager 1 and Voyager 2 are still out there, still moving, still transmitting, and scientists are still combining data from both spacecraft to try to build a complete picture of a region of space we have almost no other way to study directly. We can look at other stars from Earth with telescopes, we can model the interstellar medium with computers, but there are only 2 points, 2 single needles, that have ever actually been out there physically measuring what that environment is really like. And because those 2 needles cross the boundary at different places and different times, comparing their data has become one of the most valuable tools scientists have for understanding the true shape and behavior of the bubble that surrounds our entire solar system. This is exactly why mission scientists have said, in their own words, that without the new data from Voyager 2, they wouldn't have known whether what they saw with Voyager 1 was characteristic of the entire heliosphere or just specific to the one location and one moment in time when Voyager 1 happened to cross. A single sample can never tell you if you found a pattern or a coincidence. It takes a second, independent measurement, taken somewhere else under different conditions, to know the difference. That is the quiet, unglamorous truth sitting underneath every headline about this discovery. It isn't really about Voyager 2 outshining Voyager 1. It's about what becomes possible only when you have 2 working instruments instead of 1. Recent research building on both spacecraft's data has continued to reveal just how complicated this boundary really is. Scientists studying the region beyond the heliopause, the area researchers now call the outer heliosheath, have found that the interstellar material out there isn't just sitting still and undisturbed. It's being compressed, heated, and shaped by its ongoing interaction with the bubble our sun creates as it plows through the galaxy. Both spacecraft, now well past 140 astronomical units from the Sun, continue to detect small traces of the Sun's influence even this far out, meaning our star's reach extends even further into interstellar space than early models predicted. Every year that these 2 aging spacecraft keep transmitting adds another small piece to that picture. And every year, scientists know that piece could be one of the last, because eventually the power will run out completely. So when you hear a headline like Voyager 2 found what Voyager 1 completely missed, this is what it's actually talking about. Not a hidden planet, not an alien signal. Something arguably more interesting, because it's real, it's confirmed by 2 independent NASA missions, and it's still being studied today. It's the story of 2 identical spacecraft launched weeks apart in 1977 that ended up teaching us 2 completely different things about the edge of our solar system, purely because one of them kept a single instrument alive long enough to be there, fully awake, when it mattered most. That's the real headline hiding underneath the clickbait version of this story. Not a hidden discovery kept secret for years, but a quiet, careful piece of science that took 2 spacecraft, 2 working instruments, and 6 years of patient waiting to fully come together. It's the kind of story that never fits neatly into a single dramatic moment, because the truth of it was built slowly, comparison by comparison, signal by signal, across a gap of 6 years and billions of miles, until 2 very different pictures of the same boundary finally sat side by side and made sense together. Voyager 1 will always be first, It will always hold the record for the fastest, farthest, earliest crossing into interstellar space, and that achievement is permanent. But Voyager 2 is the one that actually let scientists see what that crossing looks like. It measured the slow buildup at the edge. It measured a hotter than expected interstellar medium. It revealed a lumpy, uneven boundary instead of a smooth one. It proved that material leaks across that edge in both directions constantly, and it confirmed that a strange magnetic alignment first spotted by its twin wasn't a coincidence at all. Two spacecraft, same mission, same era, same journey outward. But only one of them was truly watching when it mattered, and that difference has quietly reshaped what we know about the true edge of our solar system. It's a difference that came down to a single working part, still functioning decades after it was built, doing its job exactly when history needed it most. Both spacecraft are still out there right now, tens of billions of miles from Earth, running on fading power, still sending signals back across the void, still teaching us things about the space between the stars that no telescope on Earth could ever show us directly. Somewhere out past the orbit of every planet, past every comet we've ever named, two 49-year-old machines, built with less computing power than a modern wristwatch, are still doing exactly what they were sent to do: exploring. Every one of the remaining instruments on both spacecraft is powered by the same aging radioisotope generators that have been quietly decaying since before most of the people reading this were even born. Engineers at the Jet Propulsion Laboratory have had to make a series of difficult, deliberate choices over the years, switching off instrument after instrument, heater after heater, just to stretch the remaining power far enough to keep at least some data flowing back to Earth. Voyager 1 has already had multiple instruments powered down permanently. Voyager 2 is following a similar path, its own team carefully rationing what little power remains so the mission can continue for as long as physically possible. Nobody knows the exact date when either spacecraft will finally go silent for good. Estimates have shifted over the years, but the honest answer from the people who work on this mission is that it could happen at almost any time, and every additional year of data the Voyagers manage to send home now is treated as a genuine bonus, not something anyone can count on. That's part of what makes this particular discovery, the one where Voyager 2 saw what Voyager 1 never could, so significant. It isn't just a curiosity about two old machines. It's a reminder that we may only ever get these two chances to directly sample the true edge of our solar system with working instruments. There is no mission currently in development that is scheduled to repeat what the Voyagers did. Nothing is being built right now to fly out to the heliopause a third time with fresh, modern sensors. If both spacecraft go silent tomorrow, the direct, in-person data they've already sent back may remain the only first-hand measurements humanity has of that boundary for decades, possibly longer. Every reading, every plasma measurement, every magnetic field alignment, every leak detected crossing that border in either direction becomes more valuable with each passing year, simply because there's no guarantee anyone will be able to go back and check. It also helps to understand just how slow and deliberate the process of getting this data back to Earth actually is. Both spacecraft are now so far away that a radio signal traveling at the speed of light takes roughly 20 hours to reach Voyager 1 and around 18 hours to reach Voyager 2. That means every single command sent from Mission Control takes nearly a full day just to arrive. And the confirmation that it worked takes another day on top of that. Scientists aren't watching these discoveries happen in real time the way it might feel from the outside. They're piecing together a story that unfolded weeks, months, sometimes years earlier, one faint radio signal at a time, using antennas so sensitive they can pick up a transmission barely stronger than the power of a refrigerator light bulb, spread across billions of miles of empty space. Every discovery described here had to survive that entire journey, arriving as a signal so weak, it's almost a miracle, it can be reconstructed into usable numbers at all. And somewhere in the data they're still sending home right now, as both spacecraft continue drifting further from everything familiar, there's a very real chance more discoveries like this one are still waiting to be found. Scientists are still combing through decades of readings, still comparing what Voyager 1 sensed indirectly against what Voyager 2 measured directly, still building models of a boundary that keeps turning out to be stranger, lumpier, and more porous than anyone expected when this mission first launched back in 1977. Two machines, sent out with a 5-year primary mission to fly past Jupiter and Saturn, have now spent nearly half a century teaching us things about our own solar system that no telescope, no simulation, and no mission on the drawing board could have shown us any other way. And as long as they keep transmitting, even a faint signal crawling back across billions of miles, the story of what the Voyagers found, and what they're still finding, isn't finished yet. There's something worth sitting with here, beyond the plasma readings and the magnetic field data. Both Voyager spacecraft carry a golden record bolted to their side, a physical disk containing sounds and images meant to represent life on Earth, greetings recorded in dozens of languages, music selected to capture something true about who we are. Nobody expected, back in 1977, that these two machines would still be transmitting real scientific discoveries almost 50 years later. They were built for a 5-year mission to fly past 2 planets. Instead, they kept going, kept working, kept finding things nobody had planned for, long after the engineers who built them had retired, and in some cases, long after those engineers had passed away. Every new finding that comes out of Voyager data now is, in a very real sense, a message from an earlier generation of scientists who never got to see how far their work would actually travel. And that's really what separates this story from a typical piece of space news. This isn't a discovery that happened yesterday, packaged and forgotten within a week. It's a discovery still being unpacked, still being cross-checked, still generating new research papers years after the actual crossing took place, because 2 aging spacecraft, launched during a decade when calculators were still considered advanced technology, are still out there right now, doing science no other mission on Earth is currently capable of doing right now, in this exact moment, as these words are being read. That's the real reason this story keeps resurfacing. Not because something new happened overnight, but because the deeper scientists dig into what Voyager 2 saw and Voyager 1 missed. The more they keep finding, and the more they keep finding, the more it becomes clear this story is far from over. Ike taught me Thai.